Welcome back to Inference Time Tactics. Today you have me, Calvin Cooper, our co-founder and COO, and Byron Galbraith, our CTO, breaking down what we've been building, what we're learning with the launch of the thinking algorithm Leaderboard, and where we see the market heading as inference time compute becomes mainstream. This is a behind-the-scenes conversation about the engineering, the research, the market signals we're hearing from enterprises, and why this shift towards thinking algorithms is happening now. So let's dive in. Byron, do you want to start by framing what is the thinking algorithm Leaderboard and why we chose to build this now?
Sure. So we're really focused on exploring the idea of these inference time compute strategies. And we wanted to pick up a task that seemed to be relevant to businesses. So a lot of the test time compute work has been done thus far on solving like algebraic reasoning tasks or, solving really hard math problems, and also trying to do it in sort of a single model perspective. And this is still where work is kind of largely focused today. But we wanted to tackle the problem of addressing, well, how do companies actually leverage these techniques to solve their actual business problems? And do they actually translate from, say, getting a little bit better at solving math problems to actually solving, say, business tasks like generating SQL queries or things of that nature? So we started by picking a data set benchmark suite from Salesforce research called CRMArena-Pro. And this is a large number of different tasks that sales reps or customer support reps might engage with when working with their CRM. And so the idea would be, okay, you're an agent, you're trying to resolve some sort of ticket, or you're on the phone and you want to get data quickly out of your CRM. Why not have an agent do it for you? And so that's the kind of high level idea of the data set. But then we really wanted to look at this idea that you have lots of different techniques. So the simple approach would have been, prompt engineering. And that's not even that simple. But the idea was, okay, we are going to figure out some sort of extensive prompting. We are going to run it against a single model, and we're going to hope we're going to do well. In this case, you can't do that because these tasks require an inherent tool use step. They have to be able to make a call out to a database, the CRM, via API calls or what have you. And then they have to take that result and they have to then answer that question with that data. And so we wanted to sort of apply some of this space of test time compute strategies, things like best of n sampling, sort of reward modeling and feedback, self-consistency, and then just standard chain of thought style ideas. Like, how do we apply that to this task? And then can we look at the space of techniques along with the space of models? And now you get this very quickly problem of combinatorial explosion. The number of choices, the number of knobs and levers you have at your disposal gets out of control very quickly. And so we wanted to start by just sort of surveying a bit of the landscape on some of the more common approaches and just get a sense of like how impactful is this really? And so what we did is we built out sort of an experimental backend runner that would allow us to specify these sorts of experiments. So are we doing a chain of thought experiment? Are we doing a best of n experiment? How in the best of n experiment, how are we actually deciding which of the n tasks we're going to choose to actually get submitted to be answered? And then, all the different hyperparameters. So like what temperature is it using? Are we doing like token selection? Just what model is involved? What model is being used to judge results if we're using that? So we picked a handful of these and we ran them across 10 different models that were available in AWS Bedrock. And we did this for a couple reasons. Primarily, though, the idea is that if you're, say, interested in building something that is sort of contained inside of your VPC or your otherwise deployment, you're not just sending everything out to, say, an OpenAI or Anthropic. These are the kinds of models that you would have at your disposal ready to go. And it represented a nice mix of proprietary and open source models. It definitely was not exhaustive, but it did give us sort of a high level idea of some of the world today. And so we ran a large number of experiments, and then we plotted them on the leaderboard.
Yeah, and this is the first leaderboard that compares not just raw model performance against each other. It combines models with these thinking algorithms that Byron mentioned. What were our results? What surprised you the most?
Yeah, so I'll first start off by saying we've run a number of experiments. Not all of them have been published on Leaderboard yet, and so I'll share some of both what's been published and what we've sort of been seeing a little bit behind the scenes as well. So first, the main thing we saw, and we were kind of hoping to see it honestly, and we did, which is great, which was this jagged frontier, this idea that no model is a universal winner, and not just no model, but no strategy is a universal winner on these tasks. And so if you had to pick, if the current way you're building out your POC, or you're trying to think about building sort of agentic systems for some business task, if your main focus is just on, say, picking, GPT-5 and then trying to prompt engineer your way to success, what we found is that is not going to succeed. That different tasks, different requests, different things that you want to do, maybe the difficulty of things within those tasks, different models perform differently. And to the extent that you might have a subtask that works really well, and so you'd be like, great, I can deploy this specific piece of the interaction. Say, I'm trying to think of the specific task that comes to mind, but you pick one of these business tasks, and maybe that one by itself does really well. You get near 100% performance on the task, and you're like, great. But then another one gets barely 50%. And so now you're in a world where you're trying to figure out why and how to balance this. And if you can't hit a certain average success threshold of, say, 70+%, users just won't use it. They'll realize it's not successful most of the time. It's not worth their effort. And so really what this showed was not only just one model, like different techniques. We saw cases where the best event approach actually worked better from a pure accuracy perspective than, say, the chain of thought association or approach. We saw that different sampling strategies of the result from the best event also had an impact depending on the task. Different models worked differently, different levels. So I'll say that our initial findings found that the GPT 120 billion parameter model actually worked pretty well. So like if you really, really had to only pick one model, if you're like, I refuse to have more than one model and one technique in my system, then using a best of n sort of approach where you did a small number of n, we did n equals 3 in this case, actually will get you a decent level of accuracy across the various tasks. It wasn't great. I definitely struggled on some and was not the best. But it was like, okay, if I really, really, really don't want to have to think about this, and I'm okay with losing a lot of accuracy, then that would work. But what we found is that it was a mixture of the 120 billion. The 20 billion model actually worked better on some tasks. The Quen models, the larger mixture of expert Quen model tended to do well on some tasks. But again, it was never a winner take all. In fact, when we did the analysis, if you wanted the absolute best performance you could get across what we studied, it was 5. It was an ensemble of 5 different systems of models and methods, got you upwards of 72%, versus say 62%, 63% of just a single system approach across these tasks. So that was a nice finding, that there really wasn't a single solution here. If you care about things like latency and cost now, suddenly these, you've got extra constraints. These things did move around a bit. And so suddenly, because while the 120 billion model, GPT model was pretty successful, it's a bigger model. It's going to be slower than sort of comparable small models. And so kind of mixing and matching and finding different things would work better for you. And so there was one case, for instance, cost, I'll say the cost difference of the models we tested within Bedrock weren't really significant. Honestly, you could go with the best performing ensemble. And then if you wanted to save money, we would say, well, okay, the next best performing ensemble that maintained 80% of that top performing one, you would lose about 10 points of accuracy. So you'd go from about 72 to 62%. And in doing so, you would save a grand total of 0.8 cents per task. So maybe there's a certain scale at which that really does matter, but I think for a lot of use cases that may be like just a non-issue. Where the decision does come up was in latency. So we found that you could also do the same analysis and say, well, okay, if I want to stay within 80% of the best performing ensemble, but I care about latency. What can I do? And there we saw that you could kind of drop down to an ensemble of two models again, but you would end up saving like 20 some odd seconds per task. Because again, in this scenario, you have many calls that have to, they go to try to do a thing, they fail, they get to try again. There's just inherent latency in calling these things. And so that was a pretty remarkable time saving. So you'd go from something that could take upwards of a minute, or more per task on average to something that could save you about 20 seconds. And so, you take a fairly decent accuracy hit, but you also get a good benefit on the timing. So there definitely are these trade-offs. And again, different models, different systems make up those ensembles. So as a user of these systems, you do really want to know, what are your operational constraints? This matters way more than just like blind accuracy. And that may be kind of what you focus on in the POC stage. So that was sort of the nice summary of some of the findings we found with the stuff that's been published so far. I will highlight a couple sort of interesting things we took away from doing some of the additional error analysis and exploration of some of the data. So GPT 20 billion, the OSS version, often did performance-wise similar to the 120 billion on some of the tasks. And this was kind of, like, wow, okay, great. Why not just use that? It'll be faster. But it turned out it wasn't. It cost about the same, and it was actually the same speed or slower. And so that was, initial surprising. When we dug into it, it turned out that the 20 billion parameter model was just very token inefficient. And so this is another sort of hidden element to this. So while it was theoretically faster and cheaper, it took twice as long and generated like twice as many tokens as the 120 billion parameter model to get about the same level of accuracy on things. And so the cost or the latency benefit vanished. And so while the 20 billion parameter model did seem to work well on its own, in some cases, it rarely had a major benefit, in some of these other tasks because of this, I guess, propensity for the smaller models. We've seen the smaller reasoning models tend to think more. They tend to overthink. This is a very common problem with the reasoning models, especially the small ones. And so trying to balance that requires additional, levels of optimization. The other thing we found that was sort of related was we were looking at a different technique where it was sort of like self-correction. Sort of the model would produce a result, and then you sort of ask the model again, hey, does this look good to you? And then, maybe it will keep it, maybe it'll revise. And in that experiment, we did look at a couple different types of models, and including in this was GPT-5 Nano. And that the GPT-5 Nano model actually did somewhat well on some of these tasks, but it tended to be very slow. And which was surprising, but again, it's more of a capacity issue in that case. So while the model is smaller, because you're going through OpenAI and they're having to sort of, rate limit and gate people based off of their usage and their propensity to pay, you now run into some of these challenges about just getting throughput if you're trying to use a very popular model. And so, but we did find that it did fail like catastrophically on one of these subtasks. It just couldn't do any of them right. And that was surprising. And so we looked at the errors, like where was it falling down? And it turned out that it was trying to generate SQL to get data out of the database, and it just couldn't get past that phase. And what happened is that it actually was getting it right. Like you could see that it understood. It was able to generate what looked like the correct query. The problem was it wasn't following the directions well. And so our setup kind of has this requirement if you're trying to use tool use, if you're trying to get the system to do something like generate SQL, it has to produce it in a way that the system can identify where it is and pull it out to then execute it. And in this case, it was being very verbose and describing all of the reasons like why it chose the query and all this stuff. And so for a like person interacting with the system and then saying, okay, I want you to tell me why you picked this answer so I can go put it into something else, that was great. But for a like in the critical path system where I want the agent to produce this executable statement that then gets run, this was terrible, and so you don't want this. And this is actually so you could approach this in a couple ways, optimizations. One is you really have to do additional prompt engineering just for GPT-5 to say like, no, I do not want you to tell me like why you made these choices. I just want you to give me, please follow the directions, put this thing into these tags that I can extract easily. The other is to sort of look at, again, it kind of ties to with where OpenAI is going with like the GPT models, which seems to be it's clearly more for conversational interaction. Seen by like the 5.1 announcement, it made it more playful. They're like, great. And then I was thinking like, I don't want playful SQL. I want correct SQL. And so I think that it does show that there's also this expanding world of models and what they're for, and ones that tend to be really geared toward sort of chit chat or direct, human computer interaction, and others which are you're trying to put in the critical path of some operational flow. And so that also kind of can drive which models tend to do better, or how you have to think about how you approach prompting of these models. And again, these are all things we found just from this small survey that we've done so far, and relatively small, and we're like continuing to look into these things. Last thing I'll say about all of this is related to the comment about slowness of GPT-5 Nano. We also tried to explore a lot of the Anthropic models via Bedrock, and what we found there was that we couldn't use them due to throughput constraints. We weren't actually even hitting like quota limits within Bedrock, within our account. We just couldn't get the capacity. It did seem like, from our experience, that the endpoints in AWS were just so in demand, across all of their serverless endpoints that, even with like account level quota headroom, we were still hitting timeouts or, unavailable resource issues. And so we kind of stepped away from trying to study those models at this time, and are going to kind of approach it in a different direction. But it also leads to this idea that when you start to try to run things at scale, at some volume, there becomes additional things that have to come up in terms of, okay, can I even use these endpoints? How do I think about serving these models? Or how do I think about where I get my inference from? Because I might not be able to get the throughput I need for the scale that I need.
Absolutely. And let's talk a little bit about the timing. So we'll be interviewing Sean Rogers with Bark on another episode. But what we're seeing in the market, and the research shows this, is that over half of enterprises have full or limited production agents. And I really question like the scope of these pilots and things in production. People are still struggling to get AI systems to work, to be accurate and perform and scale up. But the ones that are more AI sophisticated are deploying multiple models in their system. And so they're starting to hit all these issues that Byron talked about. So this isn't just an academic endeavor, thinking algorithms plus models, what will be most performant. It's really solving an enterprise problem, something that people are facing today when getting these systems to work. So next, I want to ask you about the research direction. Like, where do we take the leaderboard from here?
Sure. So, this is a great timing because I just came back from NeurIPS 2025 that was in San Diego, and there was emphasis, a decent amount of emphasis on these sorts of strategies. There was a whole tutorial about test time compute strategies. There was a whole workshop about efficient reasoning, and then papers throughout the main conference that sort of were looking at different ways of addressing efficient inference in many, many dimensions, all up and down the stack, from like, how do I do better token prediction? How do I stop quickly? How do I, do this prompting in many different ways? How do I fine tune down to smaller models? Lots of stuff. So for us, I think, key directions going into NeuroMetric, and I think still continuing afterwards, because it kind of reinforced the idea that we were looking at, is it's really going to be about a few things. One, again, how do you do this constraint optimization? How do you, think about multiple ensembles as well? So, budget-based constraining is an area of research that a few labs have been exploring algorithms and strategies around. And they find that you can get value out of this. And I think that's something that we're also looking at, which is, again, that combinatorial explosion of places to search. You just can't, it's totally inefficient to try to search everything. So how do you do that intelligently? How do you search all those different options? How do I not spend, hundreds or thousands of dollars running GPT OSS 120 billion experiments or GPT-5 experiments or Claude experiments when I feel pretty confident that, changing temperature isn't going to do a whole lot, or, changing the context window size is not going to do a whole lot. And so one thing we need to look at is, how do you search the space efficiently? And people have done this in a few different ways. Classic ways are sort of Bayesian optimization. But it seems like something I didn't realize but was fascinating is that people are using more large language models. They're using the LLMs to do everything, including search space optimization. And so, can you sort of feed in sort of the previous results to an LLM and then say, okay, which parameter should I choose next? I need to dig more into how that works, but it's fascinating that people have started to use this and they're trying to deploy it in this space of, okay, I have so many models I can choose from. I have so many strategies or parameters to the strategies I can choose from. Which one should I choose? So there's definitely a direction we're looking at there. We just are definitely going to be running a lot more of these experiments on the CRMArena task. We still feel really excited about that task as a meaningful proxy for sort of a real world use case. Again, the idea that you've got some multi-step interaction, that's not just how much can I pull out of the model by itself, but more like, no, I need you to do multiple things. Either that's multiple agents, two specific agents that have to talk to each other and they both have to be efficient, or one agent that has good tool use and reasoning capabilities. So how do you even think about these multi-structured, multi-hop problems? Again, there's research in this area for Q&A, for tool use that's just emerging. And so we need to leverage some of that as well, and to think about how do we get these sort of ensembles of systems. So again, moving from, single model, single prompt technique to lots of different techniques, lots of different models, possibly multimodal models. This idea of task identification is another one. So, we have the benefit of, again, thinking about the pragmatics of the world. So a lot of benchmarks today, and people, not the first, not the last person who's going to say that benchmarking and LLMs is a problem, but they don't, again, often do well as good proxies for business use cases. So again, how well does a model do on abstract reasoning tasks doesn't necessarily say anything about how well it's going to do on generating SQL queries or being able to answer data analysis problems about, sales targets. There's a proc, it doesn't say nothing, but I think it also is not necessarily a strong indicator. And so you have to run these experiments. And so we want to look at, also, again, we mentioned in the results, where I was going with this, is the task separation. So we have CRMArena. We've chosen 8 of the tasks. There's many more tasks in that suite, but we focused on 8 of them that kind of span business skill use, business scenarios. It'd be really interesting to see, can you identify the problems without knowing what they are in advance? Right. So this is sort of the benchmark tie-in, which is, if I already know what I'm doing, if I know that I'm trying to solve, multiple choice algebra questions, or I'm trying to do, mathematical reasoning problems, or I know that I'm trying to solve, activity prioritization or case routing tasks, I can kind of, as we plotted them sort of based off of that dimension. But if you're trying to deploy a model from scratch and you don't necessarily know how your problem domain should be split up, I think there is a really fascinating area of research that's starting to happen in a few places, which is, how do you do this in a streaming, unsupervised fashion? how do I know what those task boundaries are? And in identifying those clusters, that can help identify the ensembles that you need to use. And so, this becomes important when you're trying to build a system that maybe, you don't have thousands and thousands and thousands and tens of thousands of samples to be able to really fine tune the results. Related to that, how do you get that data if you can't find it, is synthetic data generation. And so if we're looking at trying to identify these things or gauge the value of a discriminator, when you have very, very limited data, there's a lot of exciting work going on in synthetic data generation and how well it can work. And I do think that there's a lot of application here as well to business tasks that we could find a lot of value in. And then I'd say finally, another thing that we're very, very excited about is once you do all of this, how do you then say, cool, how do I actually take those tasks and, compartmentalize them down into a very focused, dedicated small model, for instance? I don't need to send everything to the biggest model. Some stuff will probably still need to go there if you just can't make it work. Or while you're doing your POC development, it makes sense to kind of go to the highest, most capable model that's out there. But once you sort of have identified the inputs and the outputs and what works and what doesn't, you don't need the whole capability of like an everything machine. You just need a thing that can do whatever sliver of tasks that you need for your particular use case. And so this is where the small language model compression ideas get very exciting. And again, there's some early promising work in this area as well that we're very actively pursuing.
Really excited to share more about that in the coming weeks. But before we wrap, do you want to talk a little bit about how people should be interacting with the leaderboard, what they can take away, and how they can best engage with us?
For sure. So the leaderboard right now is at leaderboard.neurometric.ai. We'll be continuing to add more results as they come in and as we validated them. It has sort of a nice initial overview of just sort of a strip plot that shows by task all the different models and systems that we've explored and kind of where they fit in there. We've added another view that lets you kind of see more of a task, as opposed to splitting on the tasks and the performance, you can split on the models and systems. You can kind of see how they all kind of interact with each other. And that kind of gives another nice sort of holistic picture of how some models tend to work well on certain tasks and certain methods versus others. And so that's sort of a nice, just, exploratory tool that we have. We definitely are interested in taking, feedback. And so we have a feedback form on there that you can fill out, or you can reach us directly. And yeah, it's just something that we're going to continue to publish more data as it comes in. And we'll just see, and we'll continue to update some of the best results. Like, we did some analysis and we had to be like, okay, if these were your systems, this is what you should choose. But as more results come in, those will obviously get updated as well.
Yeah. And we don't talk enough about the engineering challenges that go behind building products like this. I mean, it's extraordinarily complicated. Tons of decisions had to be made. And then summarizing the results was a whole challenge. So good work on that. With that, we'll wrap this episode. Be sure to like, share, and subscribe. Thanks for joining us at Inference Time Tactics.